Hello, everybody. Welcome back to another math video. So today what we're going to be doing is a bit different. We are going to be going over the triangle sum theorem. Let me just write that down if I can even write. Triangle. All right. Sum theorem. I'll just put th for the time being. Okay. So what is the triangle sum theorem, you may be asking? So the triangle sum theorem is pretty much a theorem that states, let's draw a nice triangle right here, that all three angles in a triangle is equal to 180 degrees all of the time. Now each angle may be different. For example, it could be a 30, 60, 90 triangle, 30 degrees, 60 degrees, and 90 degrees, or it could be something completely different. So now you know what a triangle sum theorem is. Let's dive further into how useful it is. All right. So the triangle sum theorem, you also need to prove it. Right, so in this example, we're going to be doing a two-column proof. So a two-column proof is usually where you give your statements. Right, let's actually drag this down here. So here, you just give your statement on one side, and then on the other side, let's just draw a line right here. You give your reasons for each and every one of your statement. All right. So now let's get into how to actually solve this. So first, you'd actually need a figure, right? It kind of makes sense you would need a figure to do this. Let's just go plop a. Let's put a blue color, something different. So let's have that right, and then so you would have a nice brush, this angle, and then this angle, and this angle. So let's just label these angle A, angle B, and angle C. So for our first reason, what we would want to do is actually draw an auxiliary line. So for those of you who are wondering what is an auxiliary line, well, here is the simple answer. An auxiliary line is an imaginary line that you pretty much draw on a figure to help you in usually a two-column proof or such as. So let's draw the auxiliary line here. Oh, it's a bit hard. Yeah. So that's the auxiliary line, right? And it is parallel to AB. It's the first statement. One, you can put in, let's put it in green, a nice bold color. Draw an auxiliary line parallel, so you can actually just put that as a parallel to line AB, or segment AB. Segment AB on triangle, I cannot spell, ABC. Right, pretty simple. And then you have the reason for it. The reason for it is this other theorem, which is called through any one point outside of a line, it forms a line parallel to, let's actually increase the space if we can, parallel to a given line. So for example, here we are, let's add another point actually on here. Let's add a point in purple, get kind of bright. So this is on the auxiliary line, and let's label this point D. Alright, and let's assume that this angle right here, this one between the auxiliary line and the triangle, is angle 1, and this is angle 2. Let's also give these names 3 and 4. Alright, so next, as you guys can pre-see, it's obvious, so let's also label this as 5. That angles 1 plus 3 plus 5 actually are a supplementary angle. And a supplementary angle is any angle whose sides add up to 180. And so 180 is usually a straight line, as you can see this auxiliary line is, right? So then that would be our second statement. Just write that as well. Statement number 2. Alright, so let's actually reduce this size so we can fit a bit more in that same area. So, angle. Alright, I cannot spell right now. Angle 1, angle 2, and angle 5 are supplementary. Then, a semicolon, or then actually we can go on to write the reason first. The reason being, pretty much the reason would be angle addition postulate, my bad. Angle addition postulate. And now the angle addition postulate is pretty much a postulate that states when you add two or more segments together, or angles together, in this case it is the angle addition postulate, you get a certain number, right? Or in this case it would be supplementary angles. Now we can actually replace this, and then let's also type, and supplementary angles, as I have previously said, add up to 180. So you can do angle 1 plus 2 plus 5, and you have to put the angles between, so let's just put angle and angle and measure of each angle, but it's going to take up too much space. 180 degrees. Right, pretty cool. Simple reason for that, it's just a definition of supplementary angles, right? So then after that, you can actually go and let's actually extend these lines further. Let's actually extend this blue one. Yeah. So let's so put this line right here and extend it, and let's also extend this line over here. All right, so pretty much, what happens with this is that we actually go ahead and then you can actually see how angles 1 and 3, as you can see, are actually pairs of alternate interior angles, which means they are both interior, right? As you can see, they're on the inside of these two lines, but they're on the alternate sides of the transversal, which is a line that cuts through this pair of parallel lines. And there actually is a theorem that states that if there are a pair of parallel lines, right? In this case, let's just put CD and AB, and they're cut by a transversal, then the alternate interior angles, in this case 1 and 3, as well as 2 and 4 respectively, will actually be congruent. Let's also write that on the side. And then you can actually just type that out. Matter of fact, that angle 1 is like congruent. That's just the best I'm going to do because there's no shortcut for it. To angle 3, and then semicolon, angle 2 congruent to angle 4. Reasoning for this pretty simple, right? The theorem that I just dictated is actually call you. It doesn't have a name, so you just have to type it out. If two parallel lines are cut by a transversal, then they form a congruent alternate interior angles, right? So now you can actually put in the substitution property here. So you can replace angle 1 with angle 3 and angle 4 and wait, hold up, wait a minute. Yeah, and then angle 4 with angle 2. So that way, your next thing would be, just type it out, angle 3 plus angle 4 plus angle 5 equals 180 degrees. Reason for this would be the substitution property of congruence. Substitution property of congruence on steps 4 and on steps 3. So 3 comma 4. And let's just, all right. So this is pretty much a proof for this theorem, and hope you guys did enjoy. This is one of my fast videos and more math videos to come. And if you did find this video helpful, consider giving it a like and subscribing. See you guys in the next one. Adios.